Hello again, everyone. If you're watching me for the first time, hello again, as the first again was invalid. Get me, right? A little joke. Haha. I have added the tagline to this video that this is the right approach to solve the problem. I had made a video earlier where I had discussed an incorrect way to approach this problem. It was a learning exercise for me, and I have since found a way to correct my logical flaws. I will point out the mistake that I made in the last problem at the end. For now, let's try to go through the problem and understand it. We are given a string s and we are given a numerical value k. The string consists of lowercase English letters. What we have to do is find the length of the longest substring such that it is made up of a single character after performing at most k character replacements. Before I try to explain the problem in detail, let's look at some of the questions that I had, and they are the same as the last video, so feel free to skip to relevant parts, which for you might be the approach and the code. So we start with understanding what a substring is. A substring of G is any string that is formed by taking one contiguous run of the characters out of G. So for example, if we have a string Annabelle, Bell would be the substring of Annabelle, and something like A and E, even though it has all the letters that are in Annabelle, would not be considered a substring because they are not contiguous. So A and E together won't form a substring. Okay, so now let's look at the input size. I have tried to solve this problem using billions of characters, and yeah, that takes time. So I have not been able to solve it in less time, and I have also not calculated why that is so. I think that's a video for an entirely different topic where I understand how to solve things for larger inputs. Where am I optimizing? Is it something that could be solved using distributed systems? Or is it something totally different where it is not parallelizable? Again, my point here is that that is a video for another time. I would like to get into more detail with that. In this one, I have kept the size as moderate and it could be up to 100k. So the size of S could be up to 100k, and we can take the value of k to be a bit smaller, and it fares better when k is smaller. But in our current approach, it usually fares even for moderate size k that is less than the size of the string. Again, like the last video, we are going to make it here so that it goes till 100k and the results are decent. The last time that I tried to solve this problem, I had to go back each time I encountered a different character. This caused efficiency problems as every time I encountered a different character, I had to go back and recount everything. I have since tried to modify my approach and it is better as it doesn't cause imbalance between the time complexity when the size of the input changes too much or is very specific. So coming back to S, it will have at least one character and k could be 0 onwards. Can k be greater than the length of S? Yes, it could be greater than the length of S. If it is greater than the length of the string, we just return n, which is the length of the string. Now let's look at the approach. We are given a string Annabelle and we are given k as 2. We have to find the longest substring with the same character, and we can change at most 2 characters because k is 2. In our case, the answer will be 4 just by looking at it. To solve the problem, we will use the sliding window approach. Our main job is to figure out what the size of the window will be and return that. If we look at the question, we can see that our window size is max character count plus at most k characters. To measure the window in our code, we use 2 pointers, the left one and the right one. And the window size is measured using right minus left plus 1, standard stuff. If we compare both the window equations, the first one was max character count plus at most k, and the second one was right minus left plus 1. If we compare both these statements on opposite ends, because both are equal to the window size, so we can say that right minus left plus 1 is equal to max character count plus at most k. To represent at most k, we can write it as less than or equal to k. And if we take the max character count to the left side, the equation will become right minus left plus 1 minus max character count is less than or equal to k. This is what our valid window will look like. We start with A, max character count becomes 1, then right is n, max character count is still 1, and the window size is 1 minus 0 plus 1 minus 1, which is less than k. So yes, that's a valid window, and the max length will be 2. We are also keeping track of that, the max length. We then move the right pointer forward, max character count becomes 2, and the window is 2 minus 0 plus 1, and we subtract the max character from this, and we get 1, which is less than or equal to k, still a valid window, and max length becomes 3. Move forward, 3 minus 0 plus 1 minus 2, which is equal to k, as k is 2, still valid, max length now becomes 4. Move the right forward, now it becomes 4 minus 0 plus 1 minus 2, which is now greater than 2, so that is invalid window. Here we slide the left pointer and shift it by 1 towards the right, and we remove the count, so now the max count becomes 1. Max length so far was 4, and we have not found a better alternative, and the window size becomes 4 again. We continue this process till we reach the end of the string. We keep track of the maximum length and return that. In our case, it's 4. Whew. That was a lengthy explanation. Let's try to look at the code to make this clearer. We start with the basics, that is declaring all the variables. We have n, which is the length of the string. Then we return 1 if n is 1. If k is greater than or equal to n, we return n. We use the default dictionary from the collections module. This is to have a notion of a hash table, and it's easier for lookup. We are not using the dictionary itself because default dict is easier to initialize instead of a normal dictionary. This will track the counts of all alphabets we have encountered. We have the left pointer now, which will be 0, and we have the right pointer, which is 1. Max length so far is 1. Max count character is also 1, and we also initialize the count of our leftmost character, which in our case is A. So we will set that value to 1 in our default dictionary. We will now head over to the loop. We have the standard condition, which is we check if our right pointer is not exceeding the length of the string, which is n. We increment the character we are just seeing. For example, if we are seeing n for the first time with our right pointer, we increment that in our default dictionary in whatever characters we have encountered so far. The next logical step is to consider the count of the character with maximum seen in the current window. Normally, to do it the brute force way, we can iterate over each element in the dictionary and then figure out which element has the most count. But since we just care about the maximum value, we can just see the previous max count and whatever right came in next and consider those two. This will make sure that we always consider the value of the right character. If it has exceeded in count than the already present maximum value. If we have an invalid window, this condition is when right minus left plus 1 will be greater than k. Uh, this is when we are sliding the left side of the window forward. So we will decrement the count of that left element and increment the left pointer, then reset the max count to 0 and find out in our valid window which one has the maximum count. For our invalid condition, as we saw the equation, it will be right minus left plus 1 minus max count car, which is greater than k. So anything that exceeds k We say, oh no, invalid, and then change the left pointer, remove the counts of the left pointer, and then update the max count character by checking which one is it. But if that's not the case and our window is valid, then we consider the length of the window and update our maximum window's length. If it was more than the previous max length, which is right minus left plus 1, which is the window size, is greater than the previous max length we have encountered. At the end of every cycle, we increment the right pointer to move the window forward, and in the end, we just return the max length. In this code, we can even remove some more bits that are redundant. I added them because I thought it was easier for my brain to understand what should happen logically, and we came to that conclusion. But because we are only concerned about the max character count that we have encountered so far, we can skip resetting the max character count and let the code only consider the count when it becomes more than the previous maximum that we have encountered. If that never happens, we don't care about that. So we only look at the character counts which have passed already previously encountered character counts. So in our example for Annabelle, ANAB, so that will be the first time we get like the maximum length of 4. And because we have already come to that, and because we already have 2 as our maximum length, when we come to something like LLEE and try to change that, we won't be considering that at all because 4 is something we have already encountered and the max length 2 was also encountered. So we don't care about that. If, on the other hand, there was a case, for example, we had greater than the value of 2 here for the max count. Suppose we had 3, for example, then we would have considered adding it to our max count. Okay, a lot of rambling. Let's see some of the test cases. I have first taken into account the test cases that I used in the last video. I will share the ones that actually don't work with the last video in the end so that it's consistent. For now, let's just check out whatever we did in the last video also works for here. So our example case, which is Annabelle and k is equal to 2, and the answer here checks out and it is 4. When k is 0, the output is 2. This is the case where we just have to find the longest substring with the same characters. When k is greater than the length of the string, the output will be the length of the string. When k is 1, the output is 2 for a string of length 2. And for another edge case, when k is 0 and the length of the string is 1, the output will be 1. Coming to discuss the space complexity of the problem, let's go through the code and try to understand each component. Most of them are like standard variables with constant length that we keep iterating over again and again. The major thing that we have to consider, which might actually take up some space, is the default dictionary that works like a hash table, which will provide us with a constant lookup time. And because the dictionary stores a fixed amount of elements, we will call it taking constant space and not really dependent on the size of n, as we only have 26 letters to consider and it will not be dependent on like how large the string will go, assuming that it won't go too long since we are having only 100k characters. So none of the integer values are going to be more than that. And that can easily account into like standard int. So we don't have to consider for larger values or anything like that. So yeah, I would say the space complexity is constant. And now let's look at the sibling, time complexity. If we analyze the code, we have one loop that we need to consider where right keeps on incrementing. We have no second loop running like the last time uh, to slide left or reset left and right both. To understand the count of the window, we actually are going to shift left and then measure the size of the window and so on and so forth. And every time right is going to be incremented. So this approach doesn't change much with the size of k like the last one. So here the loop will have to run at least once, and that's it. Then the time complexity will be O of n, which is like n is the length of the string. Okay, so as promised, now I will talk about why the approach I used in the last video doesn't work and why the approach we discussed in this video works. I had used sliding window in the last video as well. So what makes it different this time and the last time? Let's try to analyze it. Last time when I had used the sliding window, it was sliding based on the different character I come across for the first time. And yes, it did work for most test cases, but it doesn't work for all the test cases. I was anchoring the left character as the main character for my loop. Everything that was happening in that current iteration was dependent on that left character. The right character was being compared to the left character. We had to find out what our next left character would be. This is all good and dandy and works well when the left character has the most frequency in that window. But what do you think happens when it's not the case? For example, let's change our enable string. So instead of having two L's, let's make it three L's. At first sight, when we look at it, we can say that the answer is 5. Three L's and the two E's besides it. But in my last code, the L won't be the anchor point as the left pointer is at E. And that is the only thing that it will check. And for the next iteration, we already moved to L. So the window is starting from L, and we don't care about the E that we have already passed through in that last iteration. And now our max count will be miscounted as it will start with L and end with E, and that will result to 4. But in today's approach, that won't happen. We are not anchoring on the left pointer. We are just considering that as the start of our window and then considering the maximum count of the character as our main anchor point. So even in this case, when the left pointer is at E and as our window expands, the count of L will exceed the count of E, and it will consider that for the window count and we will get the correct count, which is 5 in our case. And that's it for me discussing the wrong approach versus the right approach. This one works. Do not use the other one because it will not consider cases where the left character is not the hero of the string or something like that. Coming to the question section, today I was going to use like a different approach. What can we use if we take the question opposite of this? But I think like I'm going to solve it anyway for the next video, as my sister was discussing that question with me yesterday. So yeah, we'll do that. So scratching that question and putting it for another video. Today I want to ask you, how do you think we will do if we try to use trees to solve this problem? Do you think, like, can we even solve this problem using trees? Use a DFS. For anyone who doesn't know what a DFS is, it's depth first search. Can you use a different data structure to handle this more efficiently? Why was it more efficient to use a sliding window here? If you have any thoughts, please share them with me. I try to think about these things. I am not the most intuitive about algorithms yet. I'm trying. Okay, and that's enough rambling, and that's it on my end. If you like the video, please consider subscribing to the channel. If not, then also it's fine. You're not obligated to. Uh, YouTube is a large arena. I hope you find something more useful. um, or just fun to watch. Okay, until next time, sayonara.